All right, good morning, everyone. So I am Deanna Hintz. I am a professor of atmospheric science at the University of Illinois Urbana-Champaign, and I'm also the lead of the engagement and partnerships team for iGuide, and I will be chairing our first plenary session on the Frontiers in Convergence Sciences and Convergence in Sustainability Sciences. So for our first presentation, let's welcome Liang from UMCES.
Hello, everyone. Thanks for this opportunity to present our data. On behalf of my colleagues here, they are estuarine ecologists from the University of Maryland. So we are a graduate institution in environmental science. And my name is Don. I'm trained as a statistician. I work in the interface of data science and environmental science for the last decade. And I'm very happy to be here. I feel like it's an exciting place to integrate those disciplines together to find societal solutions. The first solution I need to find is how to move forward.
That's a solution button.
Okay, thank you. Thank you, sir.
So this one, yeah.
Thank you. Okay, in this audience, I don't need to emphasize this, that the data, big data area is on us. It's particularly on the field of environmental management and science. And there are a lot of resources in data curation, but unfortunately, the state of managing the data is a challenge. I talked over the breakfast with my colleagues here. There are a sparsity of data in the area of big data. We just don't have the data where we want it. And there's even fewer meaningful data when we are talking about policy making. On the other hand, there's like explosion of technology to dealing with big data. In particular, I think I just gave an example for the commercial sector. So there's this kind of potential for convergence. How do we make use of these two, the challenges versus the advances, to make meaningful environmental decisions? I'm just giving a short example here. The aquaculture is expanding in the Maryland, Chesapeake Bay. Aquaculture is a win-win situation for both the environment and for the farmers. And so there's a lot of interest in finding the optimal locations for siting aquaculture farms. And that leads to a data challenge. How can we resolve those high-resolution habitat conditions for aquaculture in those very tiny creeks in the Chesapeake Bay? I just, for like a trivia, the shoreline of the Chesapeake Bay shallow area is almost equal to that of the California. So we need high-resolution data. So we have these two sources of data to help with that. One is very high temporal resolution, but very sparse in space. We also have another data that's high, more like spatially complete, vertically complete, but it's done in a traditional way of collection, cruises, so there's logistics. We can do very high temporal resolution. How can we make the best use of both data sets to apply this to aquaculture siting? And I just want to quickly, there are approaches and pros and cons. This problem, and it's a term called data fusion, has been developed for many different fields, including atmospheric science, remote sensing, and so on. And the spatial statistical literature have many tools for combining these data using so-called kriging, and that can be done in a time and the space domain as well. But the sparsity of data is a challenge. So to deal with that, we have more like predictive approach to fuse different types of data. Here I'm applying the geographically weighted regression. It's a very solid developed approach with robust software to do. So this is what I choose. But with the development of AI and machine learning, there are certainly ways to apply that. So this is the only slide with equations. So here, this is essentially a regression approach. I'm trying to predict those high quality long-term monitoring data with the high frequency time series data. So the regression is spatially weighted, as we probably know in GWR, and it's also changing in space to account for the different sources of salinity, and changing in time, accounting for the different drivers of salinity. So I won't go into the details here, just to comment that this is those S and TE, those are the so-called additive modeling in statistical literature. They are very well developed, and there's a robust software for doing that. So this is just a matter of applying existing tools, not applying new tools. So there are some challenges, even though this is a simple problem. We are dealing with about 100-meter resolution data for the state of Maryland, and so this cannot be done on my laptop. So we need to use the computing tools. So for now, I'm just using a local processing, like a small cluster, but I'm very interested in generalize this to a bigger area and to more data sets to make advantage of those tools I learned yesterday. So here, I'm just basically divide and conquer this big region into small regions and big years into small years and do the batch processing, do the simple parallelization approaches. And the number here is just 10 gig and a few days, so need some parallel computing. So how does this approach work? Well, I just did the standard stuff. I just leave out some data as the validation set and use the rest of the data to make prediction for those locations and times that's not used in the training of the model, and then compare them and randomly to give myself a sense of how well the approach is doing. And I also tried the different specificity of the model, meaning how detailed I want the parameters to be, from, say, a few hundred parameters to a few tens of thousands of parameters. So there's a balance between the detail of the model and the data requirement and so on. So these figures just show, well, as I get more complex and not necessarily will enhance my able to predict. So as you can see here, this outlier on the right-hand side of the panel just showing the model is just over-parameterized. It's trying to catch noise rather than predict the patterns. But this kind of exercise protect me from that, so I can use a kind of balanced approach to make a prediction. So another type of validation is I use some novel sampling done by my collaborators for different purposes. And they did this just to inform the county governments how well they are doing in water quality. So they did this, but those are not part of the training data. And here I used 2 locations in the Chesapeake Bay. One location is the regular monitoring, like bi-weekly going to the sites. The other locations, we have discrete locations, but high frequency sampling. And all of these sites are one way or the other related with aquaculture development. So this validation just compare the model prediction on the x-axis with the, model prediction on the y with the observed data on the x-axis. A few things to comment. So overall, we have a match between these 2 kinds of data, but there are also quite a bit of variations. So I'm just here showing on the right-hand side the scale plot of those predictions and the variation over season, but I can imagine there are many other kinds of variations that will need to be further evaluated in terms of land use or the spatial nature. And prediction is harder with harder frequency. So here I have the validation data. It's 15 minutes, I believe, time series of salinity. So we do see some some skill in recovering the time series for some years, but for other years, the predictions are off. So again, highlighting the challenges in this kind of data-based approach when if the existing data are systematically different from the location to be predicted, we may have errors. So lastly, so this was part of the project, again, to cite the aquaculture. So one of the environmental suitability index is salinity, low salinity, that's typically bad. And the conventional approach is to build a numerical model, physical-driven model, and that's time-consuming, and given the shorelines and the high-resolution nature, that's not very easily done. So the approach like ours is very data-driven, but it's very fast to develop and deploy, and we can even do that for other variables. So this kind of map of taking 100-meter resolution over the last few years at 15 minutes temporal frequency is kind of useful for the farmers to decide what kind of creeks are better for siting aquaculture for benefit, but also where they can avoid the disturbance of the existing ecosystem, like submerged aquatic vegetations. So this is the potential application of this tool. And I just want to summarize that. So the shallow habitats where the aquaculture exists a lot of variabilities, and we have the data. And so this project is a small step to use those data to quantify those variability and make management decisions. I just applied a GWL approach and there to generate 100-meter hourly predictions. It's okay skill-wise, but there are uncertainties that can be further improved. And in general, I think the data fusion approach like this is a reasonable alternative or supplement to the conventional approach to build physical models to understand water qualities. And lastly, thanks to the reviewers of the forum, I just want to mention that the skill is a potential area of future research, and particularly with AIs and machine learnings, and how to incorporate physical knowledge into those predictive framework to enhance the extrapolation performance of those kind of approaches, a very interesting area. And from a practical side, my colleagues are also interested in other metrics of water quality. And the data are there, again, sitting in somewhere on the server, and it's not being used. So we can, salinity is probably the easiest, then the chlorophyll A, which is biologically driven, but we can try that at least to see. And lastly, that's why I was here, is just to learn how to take advantage of this data revolution and advance the CI to make this approach not only more accurate, but more accessible, more important, so the different sectors of this decision-making can feel the data, and they can even contribute to this kind of predictive process. Thank you so much for your attention.